In this lecture, we will learn about the reflection coefficient. Let us consider the transmission line which we have seen before. In practical systems, these transmission lines are not open but connected to microwave devices or microwave systems on either side. So this could be another device, this could be another device either on the left or right of this transmission line. We call the device on the left side as the source. So this is the source device and this is the load device. In microwave circuits or in general transmission lines, we have seen these two waves, V plus of Z and V minus of Z. We know that V plus of Z is the wave going from left to right, which means it is from source to load. Similarly, V minus of Z is the wave going from right to left, that is from load to source. So this wave is called as the incident wave and this wave is called as the reflected wave. So what does reflected wave mean? It means that the signal which traveled from source to load was not fully utilized by the load and some part of the signal turned back. So pictorially we can show it like this. Consider this picture where power transmitted is equal to power absorbed PA plus power reflected. By maximum power transfer theorem, we know that what we want is that the power transmitted, we want all the power to be absorbed by the load. But that is not the case, and in practical systems, some of the power is reflected. So how do we determine how much of the power is reflected? Since we are concerned about reflected power, which is at the load, let us do our analysis at the load. So this is the incident signal. So it goes to the load and it reflects towards the source. So the analysis is at the load. In general, any impedance on the line at position Z is defined as Z of Z is equal to V of Z by I of Z. So this is using the Ohm's law. Now let us expand this equation based on the equations that we already know. Since we are calculating Z of Z at load, which is the end point and also the reference point, let us take the small letter z at this point is equal to 0. So this is our reference point. Now the impedance equation can be written as like this. So Z of 0 is equal to voltage by current. Now we know that the characteristic impedance equation is given like this in terms of voltage and current. So replacing I naught plus and I naught minus with Z naught and voltages and then rearranging gives us this equation for V naught minus. Note that here Z naught and Z of 0 are not same. They are not same. So while Z naught is the characteristic impedance, this is the characteristic impedance, Z of 0 is the line impedance on this transmission line at position Z is equal to 0. So we know that at this position the line impedance Z of 0 is actually Z of L, which is the load impedance, because load is connected at Z is equal to 0 location. So this is our reference position. This ratio of reflected voltage to incident voltage, so we rearrange this equation. So we bring this V naught plus here. So this ratio of reflected voltage to incident voltage is called as the reflection coefficient gamma. Now this equation has a great significance in microwave engineering. Consider this image Based on our earlier understanding about maximum power transfer concept, we want all the transmitted power to be absorbed by the load and none to be reflected towards the source. So in this equation, V naught minus is the reflected voltage, and ideally we want this voltage to be 0. If this is 0, that means there is no reflection. So what happens to this equation? In that case, P transmitted is equal to P absorbed, which means the reflection coefficient gamma is equal to 0. So if V naught minus is 0, then reflection coefficient is 0, and this implies a perfectly matched system. And this is where the maximum power transfer happens. If say another case where all the 100% power is reflected by load and none is absorbed by the load. So in this case, all the transmitted power is only reflected back. There is nothing being absorbed. So in this case, the reflection coefficient is 1 because V naught of minus is actually equal to V plus V naught of plus. That means all the power which is incident, everything is reflected back. So in this case, the ratio, which is the reflection coefficient value, is 1. So then what is the range of the reflection coefficient? So the range of reflection coefficient is from 0 to 1. And the practical systems have reflection coefficient value closer to 0. We want the reflection coefficient to be closer to 0, and it is around 0.1 to 0.3 in practical systems.